Okay, we're going ahead and we're going to be starting our class today. We only have about 4 more classes left before the final. Okay, so this is our last few chapters. We've learned a lot, and we're going to continue on with our looking at how we can use that carbonyl to activate that site next to us, that alpha site today. But I wanted to remind you that we have a Zoom class today, tomorrow, and Thursday. Thursday, the second half, we have our group project. Our group project is going to be doing things with the chapter 19 reactions, specifically the Claisen and the cyclizations available to us there, the Diekmann and all these things we'll be talking about a little bit today, but mostly tomorrow and Thursday. Okay, so in those courses, in that, we're going to use the same concept of deprotonating that alpha carbon to create a nucleophile and all the different reactions it can do. Okay, so top hat homework for chapters 18 and 19 will be due on midnight on Thursday, and then it'll be available for review after that for you to help study for the exam. Our third exam will be over chapters 18 and 19 only, and it'll begin at noon on Friday, and it will be in top hat. I'm going to keep the same parameters I used last week since everybody got in and was able to do the exam, so that's wonderful. Hopefully it'll be as low stress for technical side of it as it was last week. And of course, we have our new Zoom meeting invite will be sent out on Monday. Okay, so that's all administration I have. Does anybody have any questions so far about any of that? Okay, everybody's muted and has their cameras off, so I'll just assume you're waving. So, okay, so we started talking about carbonyls and how that partially positive carbon on the carbonyl gave us certain reactivities. And we started with the chapters where we added to them, did addition reactions to them, and then we did those reactions where we did substitution reactions with them. And then by adding an electronegative atom, we saw different types of reactions and was more prone to substitution reactions. Okay, so now in this chapter, we've seen that we can take that partially positive carbon and use it as an electronic drawing group to increase the acidity of hydrogens on the alpha carbon. The alpha carbon is the one next to the carbonyl carbon. And so by adding more of these electron withdrawing groups, the acidity of that alpha hydrogen goes up, and so we can use weaker and weaker bases. But once we have an acidic hydrogen at that alpha position, we can deprotonate it with either a reversible base, where we end up getting our thermodynamic product, or an irreversible base like LDA or sodium hydride, where we get the kinetic product. Okay, so now what we want to do is let's see what other reactions we can do at that site, taking advantage of that acidic proton. Okay, so the first thing we did with that is we talked about how we can substitute reactions where we can add different things like hydroxys or amines there, but then we can also use it as our nucleophile. And so in this case, we've generated our carbanion as our nucleophile, and we used it for SN2 reactions to form carbon-carbon bonds. Okay. Then we started to get complicated. Okay. Now, when we have these beta dicarbonyl compounds, the key here is that you have 2 electron withdrawing groups, one on either side of that alpha carbon, making those protons very easy to remove. Okay, and if you have the right situation, such as one of those 2 carbonyl compounds happens to be a carboxylic acid, we can use that to our advantage by actually clipping off one of them, and we can get different functional groups in the end. Okay, so the first one of these we talked about was just this long beta keto acid right here. And when we had that beta keto acid, we could heat it up and decarbonylate, and we get a methyl ketone out of this, or a ketone out of this. So in the cycle one here, if you have a straight chain one, you always end up with that carbonyl is not going to move that position. It's always going to be where you had it. Okay, there we go. So it's going to stay in that kind of position right next to the end. This was your alpha carbon right here, and now your alpha carbon is at that end of that chain, okay? And the key step in that decarbonylation is the ability to form, come on, there we go. The ability to form, why are you saving image? There we go. This 6-membered transition state, okay? So that brings us up to where we started, where we finished yesterday with this malonic ester synthesis. So whenever you have this malonic ester synthesis, you have basically 2 esters as your electron withdrawing groups. You only have 1 beta carbon, and you have 2 hydrogens on that. And the great thing about that is that those are very acidic because you have those 2 different carbonyl groups on there, and so you can easily deprotonate it with a base like this. In this case, a salt of an alcohol or an alkoxy group. But then you can also, after hydrolyzing off the esters, you can remove 1 of the carboxylic acids to yield your final product as a carboxylic acid, where the chain has been extended from whatever R group you've done by a CH2 group and that carboxylic acid. That CH2 group is from that beta carbon, that alpha carbon, and the carboxylic acid is part of the diester here, but you've removed 1 of them. So in the malonic acid ester, the key here is that you're adding a methylene and a carboxylic acid group to whatever nucleophile you're attacking to, okay? Now, you can attack with 1 nucleophile or 2 nucleophiles. We learned that on the next slide, right here. So in the case of this example, we started with that same material here, and we attacked it once with 1. We made it a nucleophile and displaced 1 thing. And then we deprotonated again and attacked with a different one. But we still went through the step of hydrolyzing off 1 of those esters to yield a mono carboxylic ester. And notice that we had, this is our alpha carbon from our original material and our carboxylic acid from our malonic ester here. And the other 2 groups were added stepwise. So they can be the same thing or they can be different things, okay? But the key here is in the malonic acid ester synthesis, you generate a carboxylic acid from whatever your alkyl halides were, okay? So that being said, let's move on to a different compound. This is what we call acetoacetic ester, okay? In this case, what we'll end up doing is we're gonna end up adding a ketone to the final system by doing the exact same steps of deprotonating our alpha carbon, using it as a nucleophile, and then hydrolyzing your ester and decarbonylating, okay? In the case of the malonic acid ester, we always ended up with a carboxylic acid. In the case of the acetoacetic esters, after decarbonylation, we're always going to end up with a methyl ketone. Okay, so that's the structure you want to look for in your final product to see where that particular material comes from. And that final methyl ketone is actually this portion of your acetoacetic ester. Okay, that will appear in the product of all of your systems, and this is where you're going to attack whatever R you have. Okay, so just like in the malonic acid ester synthesis, we deprotonate at our alpha carbon here, generating our stabilized, remember that because we have those 2 oxygens there, we have 3 resonance stabilized resonance structures there, making it particularly acidic and making it particularly stable. Once you use it as a nucleophile, you generate your intermediate here, which is just like the malonic ester, except for you have this methyl ketone on one side and the ester on the other. And then if you deprotonate that and decarbonylate that, this section is going to go away, and you're going to be left with your methyl ketone and whatever you attacked it with. Okay, so let's look at that stepwise again. If we move down here. Okay, so in the case of all of these reactions, you will go ahead and deprotonate. Because you're in between two carbonyls, you can use weaker acids like ethyl, the alkoxide, the sodium alkoxide that we have here. In this case down here, we use the tert-butyl alcohol that has been deprotonated with potassium to give us the potassium T-butoxide. Okay, so the key here is that once you have taken one of those hydrogens off and substituted, you still have one more alpha hydrogen here. If you only wanted the mono-substituted product, good, you're done. You can go ahead and go to your hydrolysis step and your decarbonylation step. But let's say you wanted a more complex, more complicated system, you would then, of course, need a slightly stronger base. Just like in the malonic acid ester, the first one comes off very easily with just a nice base like ethyl sodium methoxide or sodium methoxide. But the next one here, because of sterics here, we have to use a slightly stronger base that's less nucleophilic. Okay, so most of the time in that second step to remove that last hydrogen, we have to use the T-butoxide, okay, to get to that salt. And then once you form that anion here, you can then use it as a nucleophile for an SN2 type reaction, and you'll get to your final product here, which is your ester. And then, of course, you can hydrolyze that and decarbonylate that if you want, or you can actually have it as this beta keto ester. Okay. Remember, this ketone's on our beta carbon, and we've done all these reactions on our alpha carbon. Okay, so next slide. Okay, so the thing to look for in this acetic ester synthesis is that we're going to be ending up adding a total of 3 carbons to the end of whatever alkyl chain you had as your alkyl halide that you were attacking with, and you're going to end up with a methyl ester, a methyl ketone at the end, which is this portion here. And of course, the carbon that it's bound to, that was the alpha carbon in the acetic ester. And whatever you attacked that nucleophile with is this long chain here. Okay. So you can do it 1 substitution or 2 substitutions, but the net result is you're adding this methyl ketone to the end of a chain. You're adding a total of 3 carbons to whatever alkyl halide you had, and after you do the decarbonylation. Okay, so in the ester, you add a total of 2 carbons and a carboxylic acid. In the acetoacetic ester synthesis, you're adding a total of 3 carbons and a methyl ketone. So that's one good way to keep them separated in your head. Okay, all right, so let me show you another reaction here, and I want to show you the competition or the importance of locating that ester in that, having that beta ketone in that beta position. Okay, so let's start ahead and start a reaction with our acetoacetic ester here. We're going to deprotonate that with base, and so of course it's going to deprotonate at the alpha carbon section here. And then in this case, instead of attacking it with some other just regular unsubstituted, we're going to use an alpha halo ester in this case. So remember, we can make these alpha halo esters by making the alpha halo acids and esterifying. This is going to act as our nucleophile and displace this bromine right here, and it's going to give us our intermediate here. Okay. Now, here we have a quandary. I have a question in the chat room about, so for these reactions, if the hydrolysis of the compound and add heat, you're left with a ketone. In the case of the aceto acetic ester synthesis, yes, you're always left with a ketone, okay, if you do the hydrolysis and heat step. So you're going to see something like HCl plus heat. That means you're going to decarbonylate. And a lot of times I'll actually even write in the question minus CO2 to show you you are decarbonylating, okay? So in the case of the malonic ester, you end up with a carboxylic acid after the hydrolysis and decarbonylation. In the case of the acetoacetic ester, you end up with a ketone in the system. So yes. Does that answer your question? All right, great. So it's very clear to get those, you know, how many carbons you're adding and what carbonyl leaves. Those are two very important things. So in this particular case here, when we attacked this alpha halo ester, we actually have two different carboxylic acids available to us to decarbonylate. However, only one is going to be decarbonylated because only one can make that six-membered ring to assist in the decarbonylation reaction and generate our final product. So let me go ahead and pull this up here. Okay, so in the case here, if we just did the hydrolysis step, we'll end up with a possibility of two carboxylic acids. So we have this one that was on our aceto acetate ester. And then we have one from the group we attacked, okay? So in the case here, this one right here, this ester carbon this is the alpha carbon, this is the beta carbon, this is the gamma carbon. That ketone is on the gamma carbon away from this group. However, it's on the beta carbon of the carbonyl on this group, okay? You cannot do the decarbonylation from the gamma position. You can only do it from this beta position, which means this portion, this carboxylic acid, will preferentially decarbonylate, giving you your extended, your other carboxylic acid will not be removed, only the one that was attached in the beta position to our carbonyl here, okay? So if you have two different carboxylic acids that are near that ketone, make sure that you can, that it is in that beta position. Yes, there was a hand up.
So when you're saying decarbonylate, does that mean add heat?
Decarbonylate is to remove CO2. So you're removing that carboxylic acid with heat.
Okay.
Okay, so, and the first step is to, of course, have a carboxylic acid. And then if you add heat to that carboxylic acid and it has a beta ketone available to it or a beta carbonyl available to it, it can remove CO2. And that is the step we call decarbonylation. Okay?
Okay, thank you.
All right. So in this case, even though we had two different carboxylic acids that could be removed with heat, only one had a beta carbonyl, and therefore it exclusively is the one that's removed. And therefore we end up with our product here that is our only product, because only the one carboxylic acid that is beta to it. Okay, can you label? That's a great idea. All right, let me go ahead and label each of these as alpha, beta, gamma. So I'm going to label them from each carboxylic acid independently. So I'm going to start with this one right here. And so this is our starting point here. So that makes this the alpha carbon and this the beta carbon from this carboxylic acid. Let me change ink color here. So from this carboxylic acid, this is the alpha position, this is the beta position, and this is the gamma position. Okay, see how this is the first carbon away from the carbonyl, the second carbon from the carbonyl, and the third carbon from the carbonyl? So there is no C double bond O on the beta carbon from this carboxylic acid. So it is not easy to remove by thermal decarbonylation. Okay, so actually that was great. I should have done that in the first place. That's a really good idea. Okay, so by comparison, the carboxylic acid here at the lower end in red is not in a position to make that six-membered ring. If it can't make that six-membered ring, it's hard to remove thermally. In contrast, our carboxylic acid up here at the top is in that beta position and does easily remove that material. Okay, so once we create this nucleophile from this acetoacetic ester, we can attack it with we can use it to attack a number of different substrates, okay? So let's do a different substrate than what we've done here. Up to now, we've just been displacing alkyl halides to generate martin. Let's do something else. It actually can displace, it can act as a nucleophile for other things as well, okay? So in the case of, we learned that we could do nucleophilic substitution reactions on acyl halides or carboxylic acid halide. We can do that reaction using our enolate as our nucleophile. And in the case of this compound here, we do what we do to make our enolate is to use a base. Now notice that in the case of our acid chloride, we can't use it in alcohol like ethanol right here, because it'll react with the ethanol, it'll react with water. So we have to use it in a solvent that does not have a hydrolyzable, that will not hydrolyze our acid chloride. So that's why we have a protic solvent here. That means no alcohols, no carboxylic acids, no water, okay? All of those will react with the acyl halide and it will not do the substitution reaction. So think reactions like solvents like toluene and THF and ethers, you know, things that aren't going to have water that'll hydrolyze our acyl halide here. Okay, so the first thing we do is, of course, we form our nucleophile, our enolate ion here. It's going to go ahead and attack at that chloride and displace the chloride and then reform the carbonyl. Okay, so now what we've done is we've done our substitution reaction, and now we have a total of 3 carbonyls in our compound, okay? However, only one of them is an ester, which means that we can selectively remove that one using our decarbonylation reaction. So of course, the first step for that is to go ahead and hydrolyze the ester to give us our carboxylic acid. Now, let's look at our alpha, beta, gamma thing again. So in this case here, this is our alpha carbon to our carbonyl, and this is our beta carbon to our carbonyl. Well, this is also our beta carbon, and it's another carbonyl, okay? But this is not an ester, so this group is going to stay. And this group is not an ester or a carboxylic acid. This group is going to stay. The only one we can remove is this carboxylic acid, meaning that, and we have 2 different beta ketones that it can interact with to lose that heat. So what we end up with is we end up with a diketone compound from our reaction with that acyl halide after our decarbonylation. And if we rearrange that, it actually turns out to be a beta diketone, okay? Which is interesting because now we can use that beta diketone to go and make other things, because a beta diketone is going to have very acidic hydrogens in this alpha position. Okay. So we're using that acetoacetic ester to actually generate another material that we can use as an enolate. All right, questions on that? So each step of the reaction is the same, and you can choose whether or not to decarbonylate by doing that last step, adding that hydrolysis step and the acid and heat to do the decarbonylation. Okay, So in the next chapter, we're going to use these enolate ions to do different things, but these are all ones that we can now, we've learned how to add a carboxylic acid with a CH, with another carbon to it, right, with a diester. We've added a methyl ketone with the use of the aceto acetate ester. And we've also made a beta dicarbonyl compound by using the enolate to attack an acyl halide. Okay, so we have 3 different outcomes from the same types of materials using the same steps of the reaction, the same mechanism and the same decarbonylation. But we have 3 different products we can make from them by our 3 different starting materials. Okay. And where are we time-wise? Good. All right. All right. So does it have to be esters? Does it have to be ketones? No. Okay. Let me show you all the different groups that we can use to activate those alpha hydrogens. Okay. So the step for this is any electron withdrawing group can work as long as it's not protonated. Meaning we cannot use a carboxylic acid, because if you had a carboxylic acid and you added base, it'll deprotonate the carboxylic acid. So any carbonyl containing compound that does not have an acidic hydrogen can be used. So we can think of things like our aldehydes and ketones, of course, are really good. Aldehydes have a complication, and I'll show you that in the next chapter. So we've used esters here, but you're not restricted to these, which is what we've used already. We can have this as our material. Our amide can be used as that electron withdrawing group as long as it doesn't have any acidic protons on it. So a disubstituted amide or a tertiary amide would be good. And again, our cyano group here acts as a protected carbonyl compound. But nitro is a good withdrawing group. All of these substituents, remember in the electrophilic addition chapter where we did the benzenes, all of these have a formal charge of plus on the sulfur as well. So it also acts as an electron withdrawing group. So we can use unsymmetrical systems like the example here. We have an ester on one side and a aceno on the other, but we still have these alpha hydrogens that we can deprotonate and use as a nucleophile to generate our product. In this case, it is the cyano ester product. And then, of course, it still has an alpha hydrogen. And we can do it either attack it with the same nucleophile, attack using the nucleophile on the same alkyl halide or a different alkyl halide if you wanted it unsubstituted, or symmetrically substituted or unsymmetrically substituted. So you can change your alkyl halide in the second step and it'll be different. Okay, questions on that? So when you start looking for variety in the system, you can see cyano groups or nitro groups or esters or amides, or as long as it has something that has a positive charge there, it will enhance the acidity of our alpha hydrogens. Okay. Now, up to now, we've been making these enols. We're basically trapping it in that enol form using our a strong base that'll deprotonate that, okay? In the previous chapter, we saw that we could actually protect a carbonyl by making what we call an enamine, where we remove water from the system and use nitrogen to attach to the carbonyl carbon such that it was no longer partially positive, and therefore we could protect it from other reactions, okay? So in the case of this enamine, it's actually trapping it in effectively almost the enol form, okay? And so what I mean by that is the enol form of a compound would have the oxygen, come on. The oxygen has the bond to hydrogen, and the double bond is between two carbon atoms. Okay, so if we use a primary amine, we can trap it in that effectively enol form. And so this is the enamine, and that means we can use this to our advantage. We're trapping in that form, and we can then have the lone pair come out and attack electrophiles. So things that are partially positive charge or positive charge can be done in that addition, right, in that alpha position to the carbonyl. And then when we hydrolyze it, we'll get our ketone back. Okay. So the cool thing is with this, it doesn't really matter which of these amines you use. All of these amines will make that enamine formation. It has to be a secondary amine. And notice most of these are cyclic. It's just makes it, it doesn't have to be cyclic, but they are commonly used in there. So anytime you see a ketone added to one of these primary amines, think, oh, it's going to trap it in that enolate form, and then it will react with electrophiles. Okay, let's show you an example of that. Okay. So one example of that is to do something like this. We'll take our ketone, and in this case, we have a symmetrical ketone of cyclohexanone. And we're going to take our secondary amine and we're going to trap it as the enamine. So we have our double bond. Our double bond, it wants to reach out and take things that are partially positive. Okay. So in this case here, we have these electrons are going to come in here. In an SN2-like reaction, your halide leaves as the anion. So we have that enamine will reach out and grab and give us this intermediate here. Okay, so this is our double bond has been used. Those electrons have come out to make a new sigma bond with that carbon. And then that makes a nice stable carbon-carbon bond. And then by hydrolyzing off this nitrogen using water, we regain our carbonyl compound, and we are now substituted exactly in that one position. Okay. So one of the three keys to this are we're trapping it in that enamine, which makes it active to that site and that site only. And we can only ever form that one enamine, which means we can only get substitution there once. So in the case of, if we added a base to this thing right here, we could deprotonate here or here. And if you had excess base, you could end up deprotonating one side and then the other. So in this case, we're only going to ever trap it as a single double bond, and we're only going to get single substitution on our carbonyl compound from this reaction. So let me show you again right here. So because we are only activating that alpha site with the double bond, we will only get one reaction at that site. We'll only get monoalkylation, for example. If we used a strong base, if we used a little too much base, the first reaction will give us this product here. But if it could deprotonate. It's, again, the carbonyl compound can deprotonate either side. We still have alpha hydrogens. So we can get additional reactions on the system. So the benefit of the enamine is that we trap it to have a single double bond that reacts, and we only get monoalkylation. Okay. Okay. And we can use this to our advantage when we have aldehydes, because we can, instead of accidentally hydrolyzing the aldehyde to the carboxylic acid or oxidizing it down, we can use this enamine type synthesis to make sure we only have our double bond formed in this position here. Our double bond will only form here. And again, it's not forming a true anion. It's forming this trapped double bond, and then it'll reach out and displace it in an SN2 type reaction. And once we hydrolyze, we'll get mono substitution at that alpha position to the aldehyde. Okay, so it's a really good thing to use, especially with the aldehydes. Okay. Now, we're not restricted to alkylations. We can actually do acylations as well. But again, the first step is to use that secondary amine, trap your double bond in this position. Now your double bond is your electrophile. So your electrophile will reach out and grab and displace that halide, and you'll get monosubstitution. Okay. Notice this also, in this particular case, creates a diketone, and it creates a nice beta diketone compound. Okay. And unlike if you had formed it with a base in a regular enolate formation, you'll only get mono substitution. Okay, and that is the last slide for chapter 18. Okay, so the takeaways from 18 are hydrogens that are alpha to carbonyl compounds are more acidic. We can use different bases to remove them. And once we remove them, we can use them as nucleophiles to attack a variety of substrates. Okay, questions on that? Okay. All right, well, you can either type a question in the Zoom chat, or I'll start pulling up my next set of slides here. That is chapter 19, okay. Now, chapter 19 is all about forming those enolate ions and how they react with different substrates to make different products, okay? So in 18, we showed that we can make those enolates with those dicarbonyl compounds. We had 3 different dicarbonyl compounds, and they ended up making up 3 different products, right? Our malonic ester made a carboxylic acid that was extended by 1 carbon plus the carboxylic acid. We did it with the acetoacetate, which made it a methyl ketone and extended it by a total of 3 carbons. And then we did it with where we could substitute acyl halides and give us a beta diketone compounds. Depending on how long that carboxylic acid halide was, you could have very long chains on the ends. It's not just a methyl beta dicarbonyl compound like with the acetoacetate. It's strictly limited to that beta, that methyl ketone, because you're starting with that. With the acylation, you can have a longer alkyl halide and get a much bigger dicarbonyl compound. Okay. All right, so now we're going to start with that same first step. We're going to start with the deprotonation at that alpha hydrogen position, but we're going to start with the material and actually react it with another equivalent of the same material. Okay, so let's start with that and look at what we call, these are all called condensation reactions, okay? So the reason they're called condensation reaction is we typically lose something like water or an alcohol from the material, okay? So we have a small molecule driven off from the compound, and our final product is a combination of 2 of that type of material, okay? So in the case of this example here, we call this the Claisen condensation. A Claisen condensation uses esters, okay? So if you start with an ester and add some base to it, that's called the Claisen condensation. And our first step, of course, is the deprotonation at that alpha position. And in this case, once we form this anion here, we're actually going to attack another equivalent of our ester to generate our intermediate here, right here. This is our ester. Plus, we're going to kick out one of these equivalents from one of the materials to give us our alcohol, okay? So our condensation reactions always kick out water or alcohol, and when we use esters in the system, we call that the Claisen condensation. Okay. So let's go into the Claisen condensation a little bit more, and things to look for in your final product for these are, you're going to end up with a beta keto ester from the Claisen reaction. That's the first product you get out before you hydrolyze or do anything else. You get a beta keto ester. Okay, so let's talk about that. So I said before, what we do is we create an anion, we create our enolate from our ester. That's the first step here. So if we had, let's say we have base in our system here. So in this case, we're using an alkoxide. When you use an alkoxide in these reactions, you want to use the exact same alkoxide as the ester you have here. So if you have an ethyl ester, you need to use ethoxide. If you have a methyl ester, you need to use methoxide. The reason is that because you can actually have this come in and react with this and displace it. And so if you mix your base with the ester you have, you're going to get exchange. Okay, and so you're going to get that transesterification. So you always want to use the exact same alkoxide base as the whatever ester you have here. So I just want to draw your attention to that before we got too far along. Okay, so in this case we have come on, there we go. Okay, so in this case here we have our group here, and we have an ethyl ester. So we're going to use ethyl at the alkoxide, and we're going to do that reaction. The first step we do is we deprotonate our alpha hydrogen here. Okay, once we deprotonate that alpha hydrogen, that creates our nucleophile, and what it's going to do is that it's going to attack the carbonyl of another molecule floating by. Okay, so it's going to attack another one of these, and so we're going to create a new carbon-carbon bond with that new carbonyl. So in this case, this right here was the portion that was our enolate. That's the portion that we made our anion on. And when it came in, it displaced the this OC2CH3 from the other equivalent when it attacked the carbonyl, and that left as the leaving group. So that's the leaving group we have over here. Okay. So you generated your nucleophile, and it reacted with another one of the same compound, kicked out the ester portion of it, and generated your new compound. In this case, it's a beta keto ester. So we have a ketone and that. So it's important to keep track of this portion here was the one that made the enolate. This portion here was the neutral species that was attacked and displaced the alcohol from that ester. Okay, so if you keep track of that, that'll help you understand which products you'll make from which starting materials. Okay, so let's look into this a little more detail. Okay, so the first step, and notice that I've changed to methoxide here because we changed to a methyl ester. Okay, so I just wanted to draw attention to that. First step is, of course, deprotonation at that alpha hydrogen right here to give us our initial enolate. Okay, there we go. To give us our initial enolate here. And notice when we deprotonate that, that gives us a neutral methanol. Okay, that's not the part that's extruded, that just happens when we do the deprotonation. Okay, I'll show you that next time. Now we have attack by this enolate on the carbonyl portion of a neutral species. Okay, so it's the neutral, in this case, propionic ester of this compound here. And when it does that, it does what we do when we attack carbonyls with nucleophiles. It goes through our tetrahedral intermediate, our addition product right here. So now, just like before, when we were reacting these aldehydes and ketones, we didn't have a very good leaving group. In this case, we do have a good leaving group. We have the anion that's on the carbonyl oxygen coming in, recreating our carbonyl. And these electrons are going to leave with the alcohol to regenerate our methoxide ion. Okay, so in the next step, we see that we have our carbonyl compound has been regenerated. So we had our addition and then elimination of a small molecule. and that small molecule is the alkoxide ion right here. So we've regenerated our base, okay? So let's look at the big picture here, okay? So we start with our neutral species, we deprotonate it. We gain our nucleophile here. Our nucleophile then reacts with the first carbonyl it can react with to give the addition. Then we go through that transition state and we regenerate our carbonyl compound. Yes, there's a hand up.
Sorry, I mean, you were kind of explaining it, but so for the second step, like after you deprotonate it, when you're reacting with this, do you react with another methyl ester, like carbonyl group, like
Correct.
in the second step there?
So imagine you have, very little of that methoxide in there. So you have a little bit of it reacting with one molecule of the methyl ester. And that means there's a whole bunch of other methyl ester just sitting there that are neutral. Okay, they're not charged, they don't have it. So those ones that haven't been made into enolates can then be attacked by the one that is made into the enolate. Okay.
Okay.
So imagine you only have two things in your solution. You have your methoxide solution and you have this methyl ester. And you don't have to add a full equivalent, you just add a little bit to it, and then it'll make a little bit of enolate. That enolate will react with the other neutral species in the thing, in the solution. And then when it reforms the carbonyl, it makes regenerates the equivalent of methoxide.
Okay, thank you.
So just like we learned in our carboxylic acid chapter, because we have those electronegative atoms, that makes them good leaving groups, that we end up with nucleophilic acyl substitution, or substituting on that carbonyl carbon. Okay. So that's the Claisen. We take an ester, we add a base to it, preferably the alkoxide base of the ester, and it will generate a beta keto ester. Okay, so how can we design this to make sure we end up with what we want? Okay, we have to remember where each part comes from so that we can see where our endpoint is. Okay, since the last step of the reaction is reversible, we need, it means we have, the ester must have two alpha hydrogens and an equivalent rather than a catalytic amount. Okay, what that means is we typically use it such that we don't want to form just a little bit of this in the solution with a trace amount right here. I said you only need a trace amount to get the reaction to go, okay? But what happens if you have a trace amount now is that you now have two different carbonyls that can be reacted on here. So we want to trap that dicarbonyl compound, okay? And the way we trap that dicarbonyl compound is we deprotonate it and turn it into that another enolate here. Once it's formed the enolate, it does not act as another carbonyl compound, okay? So what we can do is, and because of sterics, this is less nucleophilic than the other nucleophile we generated, okay? So the key here is we do want to add a full equivalent of that base. It's going to deprotonate, create that beta diketone compound, and then our beta keto ester compound actually has a more acidic proton on it than the starting material did. And therefore it's going to deprotonate and stop. This is going to be trapped in the solution until you acidify, okay? Once you acidify, then you no longer have base and it's stable as your neutral compound. So, and then again, you can drive the reaction to make a whole bunch of this salt here if you remove this alcohol by just distilling it off or removing it. And that's the condensate of the reaction is the stuff you're removing by distillation. Okay, so we can take any ester as long as it has acidic hydrogens and make the Claisen condensate, which gives us a beta keto ester. Okay, so one of the interesting things you can do with that then is that if you have a diester compound, you can actually react one side of the molecule with the other side of the molecule and do a cyclization. Okay, so this is an intramolecular, meaning I'm going to attack one side of my compound with the other side of my compound, and we'll end up making a ring. Okay, so the key with these intramolecular condensations is we typically only make 5 and 6-membered rings. So not all diester compounds will do this, only ones that can make 5 and 6-membered rings. Okay, so the mechanism is exactly the same as before. We have to have alpha hydrogens that are available to us. And once we form the enolate on one side of the compound, it's going to attack the carbonyl on the other side to generate the ring. So let's look at the mechanism for this. Okay, so again, the first step is forming our enolate. And unlike the previous example where that had to kind of wander around the solution to find a carbonyl compound, it actually can just swing over to this side of it here and generate that tetrahedral intermediate. Our tetrahedral intermediate now has the chance to have its electrons kick in and then kick out that methoxide as that small molecule. And notice that the structure is exactly the same. Let me just kind of cover up this side over here temporarily. So see how we still have that beta keto ester? The only difference is we've reacted on the other side of the molecule to make a ring. The same, we still made the same structure, and to give us, regenerate our alkoxide. And of course, this is going to react with our last beta hydrogen right here to trap it as our anion until we quench the reaction with acid. Okay, so there's some rules associated with this right here. And the rule is that you will only do this if your esters are 5 or 6 members apart, and you're only going to do it to make 5 and 6-membered rings. Okay, 4-membered ring is too strained, they rarely form. 7-membered ring is too disordered, they rarely form. So look for 5 and 6-membered rings available to you. All right. So now there's another way to design your Claisen reaction to be very clean and give you the product you want, okay? Now in a Claisen reaction, you're always gonna react some kind of ester, and you're going to try to end up getting your beta keto ester compound, okay? So one way to make sure you get only one product available to you is to go ahead and do what we call a cross Claisen reaction, meaning you have one substrate that does have alpha hydrogens, and then you do a reaction on something that has no alpha hydrogens, and then you can get a similar reaction to go. So in this case here, we're going to start with our ester like we had before, and in this case we only have one alpha hydrogen right here. So when we use our irreversible strong base, we're going to trap our enolate in this position here, and it is now our nucleophile, okay? So instead of attacking something like an ester or an aldehyde or a ketone, we're going to attack this acyl halide here, and our chloride ends up being our leaving group on this. And what we'll end up with is the same structure we were looking for in the other Claisen reactions, our beta keto ester right here. But instead, we're going to generate a very poor base, our chloride ion, as our leaving group. So the reaction stops at that position. Okay, it's still a Claisen reaction because we are still making a beta keto ester, but we've chosen to use it unsymmetrically. We didn't react one of itself. We chose to use a different material. And the best way to do that is you make all of your enolate first with an irreversible base, and then you add your next substrate in to make it react in that exact position. Okay, and let's go and talk about the cross Claisen reaction. Okay, in this one right here, we have done a substitution on an acyl chloride. Okay, the cross Claisen reaction is actually similar to that, but you have a total of 2 esters in your system. You're not doing that acyl substitution. You have an ester that does have alpha hydrogens, and you have an ester that has no alpha hydrogens, okay? So in this case here, we can use this substrate here. Notice it does have alpha hydrogens, and this ester right here, it doesn't have any hydrogens in that alpha position, okay? Which means when we add our base, this cannot form a enolate. It cannot form that negative ion because there are no acidic protons available to it. So what we'll do is, in this case, this one doesn't form the enolate, but the other one will. So if we form all of this compound, we put in a whole equivalent of our base here, and we form our enolate here, we're going to receive one compound out of it. It will form the enolate, and that enolate will attack the other carbonyl compound, kicking out the ethoxide in this case, or the alkoxide in this case, and generate our beta keto ester compound in a very controlled and simple fashion. Okay, so a Claisen reaction is when you use 2 equivalents of the same ester. A Dieckmann is the Claisen condensation on itself. So you have 2 esters on the same compound. You can do a Claisen using an acyl halide to generate one product only. And then we use a cross Claisen reaction when we take 2 different esters, one having alpha hydrogens, one with no alpha hydrogens. Okay, questions on that? Let's see, I think we're going to move on to another reaction here. Yeah, so what I want to do is I want to stop here, go ahead and take a 10-minute bio break, and then we're going to move on to the Aldol condensation, which is the next one. So what we've talked about here is the 4 types of Claisen reactions we have. And the Claisen reaction always produces a beta keto ester. It always starts with an ester that has alpha hydrogens. And we can do it 2 of the same molecule, 2 of different molecules, or within a molecule, or on an acyl halide. Okay, I'm going to stop recording, let you ask questions, and then we will take a break.